This video is all about energy and momentum. Hi there, you've made it to Unit 2's video where I discover the many ways that the principles and concepts relating to Physics 12 find their way into my life. Without further ado, let's start analyzing. Since exercising is a hobby of mine, and I do it almost every day, let's see how my workout routine and gymnastics training involve some of the main topics covered in this unit. First off, talking about work. In a physics sense, we learned that work is the energy transferred to an object when a force acting on an object moves through a displacement. Work uses the equation W equals Ft cos theta. This definition of work does not exactly align with the vernacular meaning, where we use work to describe an activity in which one exerts strength to do or perform something. Therefore, when looking at many of my conditioning drills, such as push-ups and squats, I could be doing work in the vernacular sense as I'm exerting strength to exercise, but in a physics sense, have I done work? Kind of. A little confused? No worries, let me explain. Looking at my push-up, yes, I do work against the force of gravity, but my net work when I've completed a full push-up is 0. The key concept is that we must distinguish between work and net work. My muscles exert a force through distance, and that sure is work. But breaking it down into the two phases of a push-up, we can see that the work has the same magnitude, but are opposite in signage. By lowering myself, the force is up and the distance is in the opposite direction, making the work negative. By pushing up, the force and distance are in the same direction and the work is positive. The net work, thus, is 0. So although I've burned calories as heat energy has been expended, in the strict sense of the physics definition, no work has been done on my body because it has not been displaced. Another way to look at it is through the formula. So since D is 0 in a push-up, work done is 0. What else is an example of 0 work in my sweat-inducing routine? Say I lift dumbbells over top of my head and walk forwards. Sure, it's a great full body workout, but because the angle between the force and displacement is 90 degrees, I've done no work. In this case, the normal force is perpendicular to my displacement, and what can be said is that the work done by the normal force on the dumbbells is actually 0. Alright, so when would I actually be doing work while exercising? Well, work is done when, in exercise 3, I'm pushing a block along the floor for my block push exercises. In this move, displacement is not 0, force is not 0, nor is the angle of the force perpendicular to the direction of the displacement 0. Therefore, I can happily say that I've done work with regards to physics. For exercise 4 and 5, let's see the application of elastic force and elastic potential energy respectively. For exercise 4, I'm doing banded hip abductions. Though it would be easier to do this exercise free of any additional restrictive bands, let's see what it's doing. With the goal of keeping this band stretched, there will exist an elastic force that acts opposite to the direction of my applied force. The more I stretch the band away from its equilibrium position, the more elastic force exists. The more elastic force exists, the more difficult the exercise is. Next up is assisted chin-ups. Unlike the previous exercise, the implementation of this band makes my job a whole lot easier. The band utilizes the basics of elastic potential energy to aid me in my chin-ups. As a hang, I stretch the band beyond its equilibrium position, which stores a lot of elastic potential energy. According to the law of conservation of energy, the initial gravitational and elastic potential energy will be converted into more gravitational potential as well as kinetic energy as I go for the exercise. For the assisted chin-ups, I apply pressure down on the band, and as I quote-unquote release some of my weight applied onto the band by pulling myself up with my own strength, the band shoots upwards. This concept takes on a similar idea to that as of a slingshot. When a slingshot is pulled back and released, the object gets shot forwards. When I push down and release, I get shot upwards. Overall, the application of these kinds of resistance bands in the fitness industry have been nothing but a positive. Along with the fact that they can either be assistive or resistive, elastic equipment is inexpensive, lightweight, and easily stored and transported. As an athlete, I use these bands daily for functional training, injury prevention, greater gains in power and explosiveness too. Although they may look deceiving, these bands have a significant purpose, especially when seeing how the physics play out. Looking at my own stash of resistance bands, you can see that they come in a variety of styles. Since these are simple ideas in themselves, why make them any more complex? Why change them if they already function at their best? Coming out of this subunit, we learned about momentum, impulse, collisions, and the law of conservation of momentum. Now, every one of these concepts can be applied to my gymnastics training. You know what? To discuss momentum and collisions, let's look at how it is applied to my gymnastics training, seeing as doing gymnastics is a part of my daily life. Momentum, in simple terms, is a quantity of motion. Here, quantity is measurable because if an object is moving and has mass, then it's got momentum. If an object does not move, then it's got no momentum. In everyday life, momentum has an importance, but many people just don't recognize it. In sports such as gymnastics, however, momentum is commonly used as a term. The momentum of a body is defined as the product of its mass and velocity. Therefore, in my gymnastics, when I'm flipping, it can be said that I flip with momentum. Another point to make is that I use the concept of impulse as I land. In gymnastics, we learn to bend our knees when we land to absorb the dismount. This is because by bending our legs as we land, we increase the time it takes to completely finish the landing. By increasing the time, we experience less of a force on impact, therefore reducing the risk of injury. With the mention of increasing time on landing, an actual application of this principle is found with the mats we land on. Since gymnasts have to land after flying meters in the air, the goal is to minimize the effect of the force on the athlete as he or she collides with the ground. The mats have been structured to be softer so that time can be elongated and thus reducing the force on impact, making landings hurt less. Though these mats have been very helpful with our landings, not much has been thought of for the rest of a tumbling line. My vision has always been to create and design a floor that can sense fear and an injury before it even occurs. When the floor senses a fall coming, it would open up to a foam pit so the collision an athlete has with the ground won't be as painful. Since foams are soft, the time of collision would be drastically increased, and the force an athlete feels would be little to none comparing to when hitting the floor. This invention of mine has the potential to save many athletes' careers, as well as ultimately push the level of gymnastics to new heights. Now that my part is done, it's up to you to venture off and discover where energy and momentum play a role in your life. Alright, see you in the next video.